I want to finish off today with talking about the rate at which nuclear reactions occur. We've looked at what types of nuclear reactions we can see, and we've looked at the types of ionizing radiation we have, the penetrating power, the ionizing power, what they consist of, what causes them, but how quickly do they occur? Well, in order to understand how quickly they occur, we have to define a new term called half-life. Half-life is the time that it takes for 1/2 of a sample to decay. In other words, how long does it take a kilogram of uranium-235 to decay into 500 grams of uranium-235? Or how long does it take 1,000 carbon-14 nuclei to decay into 500 nuclei of nitrogen-14? The problem that we have with analyzing the rate of nuclear decay is that it's a random, spontaneous, natural process. So we don't know exactly how quickly a particular nucleus is going to decay. But we can, given a big enough sample size, look at some statistics. Statistically, after a certain amount of time, half of this uranium will be transformed into something else. Statistically, after this amount of time, half of this carbon-14 will be decayed into something else. This works if we have large enough sample sizes. If you have small numbers, it doesn't work so well. It's kind of like flipping a coin. If I have 2 quarters and I flip it twice, all bets are pretty much off as to how many heads and how many tails I'm going to get, right? Statistically, I'm going to get 1 head and 1 tail. But with such a small sample size, it could easily be 2 heads or 2 tails, right? And it could easily not work out to be 50-50. But if we have 1,000 coins and we flip it 1,000 times, then we're going to end up like pretty close to 50-50 heads and tails, right? With a bigger sample size, the statistics work. So whenever we're analyzing radioactive decay, nuclear decay, we got to make sure that we're dealing with big sample sizes so that the statistics work. Now, one more thing before I move on and show you a couple equations. I'm not simplifying this for you. I'm not saying, oh, these guys are only in grade 12. They don't have the ability to understand what really happens. We're not trying to simplify this. Okay, if you take a PhD in physics, you're not going to be able to predict any better than you will be able to predict today how quickly a nuclear reaction is going to take place. We don't control it. It happens when it wants to happen. All we can do today or 10 years from today is predict based on statistics what's going to happen. And if we have a big enough sample size, those statistics usually work out. If we have a small sample size, then not so much so. A couple of equations. The first one I'm going to put over here and I'm going to star it because it's not on your data sheet. N stands for the number of half-lives. The number of half-lives that have elapsed. If the half-life of something is 2 days, let's say it takes 2 days for 500 kilograms to get down to 250 kilograms, the half-life will be 2 days. If the half-life is 2 days and 6 days have gone by, then that means I've had 3 half-lives. So to find the number of half-lives, we're going to simply divide the time that has elapsed by the half-life. And by the way, time and half-life can be measured in whatever units you want, as long as you're consistent. If it's days, that's great, as long as it's days for both. Hours, minutes, seconds, years, millennia. The half-life can range from a tiny fraction of a second to millions of years. Doesn't matter what units you use. Use whatever's convenient as long as you got T and T1/2 in the same units. Now the other equation that does appear on your data sheet is one that some of you are probably familiar with already. How many people have seen that one in math class? Exponential growth and decay. This would be decay, right? How would you make it exponential growth? Like if you're talking about compound interest. Yeah, you put a 2 there, right? The 1/2 becomes a number that's greater than 1, right? If you have a number that's less than 1, n gets smaller. If you have a number that's bigger than 1, n gets bigger, right? You probably did an example of radioactive decay, actually, of half-life when you did exponential growth and decay in math class. So this is, for some of you, going to be a little bit of a review. N stands for the final amount. And 0 stands for the initial amount. And of course, little n, we already know that stands for the number of half-lives that have elapsed. Now, n and n0 can be whatever units you want as well, as long as it indicates an amount. Sometimes it might be grams, kilograms. Sometimes it might just be a number. Sometimes it might be a percent. By the way, if it's a percent, what do you think n0 is going to be? 100. We start with 100%, right? It could be a unit called a becquerel. Don't worry about exactly why that is. It's just a unit of radioactive decay. In one of these questions, if you get a unit you don't recognize, it's going to indicate an amount in some way. So it's going to be n or n0. Use whatever units you want, as long as it indicates an amount, and as long as the initial amount is in the same units. First example, it says the half-life of a hydrogen-7 isotope is 2.3 times 10 to the negative 23 seconds. You would not need to predict this on a test, but I'm curious if any of you can predict it right now. What type of radioactive decay do you think hydrogen-7 would undergo? I'm just curious, right? It's not something you have to be able to do on a test, but this can at least partially test your understanding of what we were talking about earlier.
Beta negative.
Why would you say beta negative? Bit of a guess?
25% chance.
Sure, 25%. Yeah, what do you say? It has 1 protons and 6 neutrons. That means it probably has too many neutrons, which means it would probably undergo beta negative decay. Yeah, that's what I would guess as well, beta negative decay. Good. So the half-life is 2.3 times 10 to the negative 23 seconds. So let's write that down. We have 27 grams to start off. That's our original amount, N0. And we have a total time that's elapsed here of 1.84 times 10 to the negative 22 seconds. I mean, that's not very much time, eh? This is a really, really small half-life. But yet other times we see half-lives that are millions of years. It just depends. Depends on the stats, right? We can't make it happen any quicker or any slower. We're looking for how much remains. We're looking for N0. So we're going to say N is equal to N0, 1/2 to the little n. And we don't know little n, so the only other way we can find it, yep. Go ahead, Spencer. We're looking for, we're looking for N, yes. We're looking for N, thank you. We've got N0, right, the initial amount. How much would remain? How much is left at the end? Yeah? I'm sorry? It is grams, you're right. As long as we're consistent, it doesn't really matter, as long as we recognize that at the end, but you're right. N is, it's not N over N0, it's T over T 1/2, right? The time is 1.84 times 10 to the minus 22 seconds, divided by 2.3 times 10 to the negative 23. That gives me a little n. What does that give me? 1.84 times 10 to the negative 22 divided by 2.3 times 10 to the negative 23 gives me 8. I've got 8 half-lives here. So now we go to sub that in here. 27 times 1/2 to the 8. Watch me on my calculator for this one. 27 times 0.5. We're not going to say times 10 to the 8. That's wrong. This is not times 10 to anything. This is just 1/2 to the 8. You got to hit that little caret button there to get that. Gives me 0.10, 0.11. And of course, as Spencer said a minute ago, that would be grams, right? Let's take a look at question number 2 as well. It says the half-life of plutonium-244 is 8 times 10 to the 7 years. Well, that's a long half-life compared to the last one. By the way, sometimes you see a year written like this, Y, or sometimes you see it written like this as an A. What do you think A stands for? Annum, Latin for year, right? I'm going to make it a Y, though. How much time must pass? Looking for T for a 1 kilogram sample. This is what I start with. I'm going to make it 1,000 grams, actually, because my final amount is 62.5 grams. We could have converted them both to kilograms. It really wouldn't matter. I just chose to make grams instead of kilograms. We got 2 equations that work here. N is equal to T over T 1/2. And we've got N is equal to N0 1/2 to the little n. Rearrange this to solve for T. It's the only thing I have to solve for T. But I don't have a little n. So now I go over to my other equation and solve for a little n. How do I do that? That's, sorry? I'll say it. Logarithms, yeah. You still have to go to the other equation because we need t and it doesn't appear in that one, right? But we can use logarithms here. But how many people have never seen logarithms before? How many people don't know what I'm talking about? If you haven't taken Math 30, you won't know what I'm talking about. That's okay. There's another option. Okay? I'm going to show you the logarithm way, and then I'll show you the other option way, and then you guys can just make your choice. We're going to say n is equal to log n over n0 over log 1/2. If that does not make sense to you, what I just did, don't worry about it. Use the other way. If it does make sense, then choose between this way or the other way. Let's say log n over n0. N was 62.5 over 1,000, n over n0. Divide that by log 0.5 gives me 4. 4 half-lives have gone by. 4 times the half-life of 8 times 10 to the negative 10 to the positive 7 gives me 3.2 times 10 to the 8 years. Now, what's the other way? For those of you who have never seen logarithms, or for those of you who just hate logarithms, which is probably a bunch of you. I call it the divide by 2 method. The divide by 2 method, we create a little table. The first column is little n, the second column is big N. Little n stands for the number of half-lives. If 0 half-lives have gone by, we have 1,000 grams, because that's what we started with, right? If 1 half-life has gone by, we have 500 grams. Just divide by 2. 2 half-lives would be not 0, because we're not going down to 0 again. We're taking half of that, which is, Brennan, 250. 3 half-lives is 125. And 4 half-lives is 62.5. So by dividing by 2, we've just determined that the number of half-lives is 4. We could sub it back into there and get the same answer. Now, the benefit of logarithms is that you can use logarithms when it's not a whole number, when n's not a whole number, right? The divide by 2 method is only going to work if it's a whole number. But the good news is, in Physics 30, they recognize that not all of us have learned logarithms, so they don't expect logarithms. Doesn't mean you can't use them, but it does mean that there is that other option that will always work for you. So if you're comfortable with logarithms, go to town on them. If you're not comfortable with them or you've never learned them, that's okay. You just have one less option, but it's not a particularly hard option. All right, your homework for tonight. Your homework for tonight is worksheet number 25. Now, this is going to sound like I'm not being very nice, but there's 12 questions on that worksheet. You don't have to do number 12. So I need you to do number 1 to 11. But there is like A, B, C, and A, B, C, D for a number of them. I'm only asking you to do A for all of them. Does that make sense? So 1A, 2A, 4A, 11A, and so on. Just the first one in each one. Try to get those done for tomorrow, okay, because it's our last day. We want to get through this and onto our graph before the break.